Welcome to the Earth Data webinar. Today we have Dr. Renée Tamblyn speaking with us. So Renée got her PhD from University of Adelaide, Australia, before she started her position at the capital, Switzerland, at the University of Bern. So today she's going to talk about the TTG formation. So with that, I will give the rest time to Renée.
Wonderful. Thank you very much for the introduction. I will just share my screen. And then, all right, how is that for everyone? Can you see it?
Yes, pretty good.
Wonderful, thank you. Thank you so much for the introduction, and thank you very much for the invitation. I'm really excited to speak about this. It's some recent work I've been working on, and I'm looking forward to sharing it. So, of course, I'll be talking about TTG formation and then continental crust formation in the Archean. But I want to highlight, I've sort of added to added to my title here, a very metamorphic perspective. So I hope you all like metamorphism and petrology because you'll be hearing a lot about it. And I just wanted to say this is part of a big project, which is run by my supervisor, Jörg Hermann at the University of Bern. And it's a big project looking at water cycling in the early Earth. So I've already been introduced, so a bit about me. As you know, I studied at the University of Adelaide in Australia, which is my hometown. And now I'm lucky to be a postdoc at the University of Bern. And my research interests are kind of varied. I did my PhD very much on subduction metamorphism, including melange formation, so looking at equigates and blue schists. I also spent a lot of time doing some garnet geochronology, especially in situ, lutetium hafnium garnet geochronology. But more recently, I've been moving towards the end of my PhD, and now I'm quite interested in continental crust formation and evolution, and sort of the evolution of TTGs, granites, these sorts of rocks. And this has led me down to looking at ultramafic rocks in the Archean. So we all know all about Earth's history, and this is just a nice figure from Richard Palin et al., which I really like, which shows from the Hadean into a modern day here as a circle. And what I like about this figure is that every black arrow you see here is an estimation from some authors on when plate tectonics began on Earth. And by plate tectonics, I mean modern plate tectonics, so subduction, arcs, all this sort of thing. And as you can see, there's a lot of disagreement. There's some very young examples or suggestions. There's also suggestions all the way from the late Hadean to the Neo-Archean. And to me, this really highlights that we don't actually know when modern style plate tectonics began operating on Earth. We also don't know how. And the reason I think this is important is because the style of plate tectonics and when plate tectonics began will tell us a lot about when the continental crust started to be formed or was formed. So to think about today, the modern day continental crust is made in arcs, as I'm sure we all know. This is just a schematic here, where the downgoing plate is usually mafic in composition, it's the oceanic crust, and the dehydration of antigerite and chlorite, which are found in the ultramafic rocks, but also the dehydration of lawsonite, amphibole, and epidote in the more basic rocks, basically releases water at these sorts of conditions, which then enters the mantle wedge. This creates some sort of partial melting in the mantle wedge and creates essentially basalts. And these basalts either underplate the continental crust or actually intrude the continental crust. Either way, they result in melt and water being injected into the base of the continental crust. And this allows for continental melting and forms our arc, which is essentially diuretic to andesitic in composition. So the useful thing here is that most of the modern day continental crust is diuretic to andesitic in composition. So we can say, okay, this must be the process that's creating our continental crust today on Earth in general. But if we now look to the Archean, there's way more questions. The composition of the crust is very different back then, or what we think the crust is. And we also don't know when plate tectonics began operating. So this leads to some big research questions, which I won't pretend to be able to answer them all, but I will discuss today. which is what was the continental crust made of? How was the continental crust made? And we know nowadays on the current situation on Earth, water, free water is incredibly important in making the crust in arcs. But what was the role of water in the solid Earth in the Archean? And also a good question is, how was it transported? So first question, what was the continental crust made of? I'm sure a lot of you have seen a nice Archean craton in your time, but this is an example of an Archean craton from the Katbal craton. And basically what you can see in all the green, purple and orange is a greenstone belt, which make up small parts of these Archean cratons. But what makes up the majority of these Archean cratons are these plutons that you can see in pink colors through here. And these plutons are made of very felsic, very silica-rich material. And people have recognized this for a long time. This isn't one of the oldest examples, but I think it's a really nice example from 1969, where people started looking at cross sections of these Archean cratons. And they noticed really interesting features. Like, so these greenstone belts we can kind of see through here are infolded and squeezed. And they're squeezed between the more felsic material or the domes. And this has led to the development of what we call dome and fill structures, where it's suggested that there's some sort of very felsic crust and an overlying greenstone, which then is infolded and sort of squeezed between the domes of the felsic material. So this is just a 3D sketch to kind of like really make that point home. And in these greenstone belts, there's actually a lot of serpentinites and sediments, but I'll get to that. But the domes are made of TTGs, as we have probably heard a lot about. So these tonalite, trondhjemite, granodiorite series rocks. And it's estimated that TTGs make up around 80% of surviving Archean crust. They're very felsic, they're very silica rich. On this plot down here, you can see they plot very close to sodium, the sodium corner, so they're very sodium rich. And they would have been very buoyant, they would have been very, there would have been a lot of them. So it essentially suggests that likely that was the continental crust. It may have been above ocean level, and it would have been the most similar thing to continental crust as we see today. So how was it made? That's a question. So, okay, if the continental crust is made of TTGs, how is it made? How are these TTGs made? And there's a lot of discussion on this and a lot of literature on this. But in general, I think it's been agreed that TTGs were formed from the wet melting of basalt. So free water present during basalt melting conditions. And the surprising thing, at least to me, is that the temperatures of this TTG generation were quite low. Most of the time, free cells melting of basalt water to allow the luminous melting of basalt at these low temperatures. And this is sort of also summarized here in this nice summary diagram from Martin and Moyen. They wrote a really nice sort of look over TTGs in 2012, a nice review. And you can see what they've done here. These two diagrams here are PT diagrams. So we have pressure here in kilobars and then temperature down on the x-axis. And what they've tried to do is take experimental results of making TTGs. And they've said that these are sort of the fields at which you can make a TTG from a tholeate basalt or an arc basalt. So essentially to make a tonalite in dark blue, you have to be quite high temperature. To make a trondhjemite, you have to be relatively high pressure in light blue. And to make your granodiorites and granites, you're usually quite close to the solidus. So this black line is the wet basalt melting solidus. So this is a really nice summary, but of course that can't be it. There's way more complexity. So they've also shown that, of course, pressure makes a big difference. If you vary the pressure quite dramatically, also the presence of water, the presence of excess silica, and many more things. So while I say vaguely that TTGs are made from wet melting of basalts, it's important to note that there are many, many other processes operating. Because TTGs have very large differences in major element chemistry, such as their sodium, calcium, potassium, but they also have major, major differences in their trace element chemistry. And a lot of people have looked into that. So the differences in source chemistry, so the composition of the basalt, the melting depth and temperature, the partial melt volume, so the amount of melt created from the wet basalt melting, subsequent fractional crystallization and magma mixing, And these have all contributed to different TTG compositions. So it's important to know that it's a relatively complex story. So how do we know all of this? Well, luckily there's a lot of evidence. So I think some of the field evidence is really interesting to look at. So these are all examples where we have a basaltic rock, the darker rock, and usually a ternolite being formed. So this white material, a ternolite or a granodiorite. And this just shows really nice partial melting of the foliated basalt to create these leucocratic TTG-like layers. So this example is from Canada, this is from Venoscandia. And then, of course, if we look at the actual TTGs themselves, like this example from the Superior Craton, we often see these residual mafic enclaves left inside. So all really nice examples of that. We also know a lot about this from phase equilibrium forward modeling, and a lot of studies have looked at this over the past 10, 20 years. These are just two of my favorite examples. So here is an example from Palin et al. 2016, where these colored points here are modeled melts. He modeled a basalt melting and extracted the melt at different conditions at different pressures. And the blue dots are the natural record. So we can see that some of the modeled melts overlap very well with the natural record. This is another example down here from Northeast Australia, where people looked at the trace elements, which I think is a really nice way to do this. So in gray, you can see the trace elements of an example TTG that the authors studied. And in color, you can see modeled melts. So they did all the trace element fractionation and worked out exactly what would be in the melt. And on the left here, we have an example of fluid absent melting, so no water. On the right, an example of fluid flux melting, so pumping free water into the melting system. And basically, they surmise that different degrees of melting can explain different types of TTGs that they looked at. So really neat studies, I think. There's also some experimental evidence, some really nice experimental evidence. So here's a nice example on the left of an experimental setup showing basically the produced things from melting crushed up basalt, which I think is really cool. So you can see the relics orthopraxine, plagioclase, and amphibole and ilmenite. These would have been like the cumulant minerals or the minerals left behind, and then the TTG melt, which is created. And then on the right here, we have a study which I think is really important, because this, for me personally, really nailed down the fact that TTGs are formed at fairly low temperatures. So this is a titanium saturation experiment from Xiong et al. And basically what they have here is titanium content in weight % on the left, so in the bulk rock. And what they show is experimental conditions of titanium saturation. And that's these are white circles through here. And then the gray dots in the background is a big natural data set of TTG compositions, the titanium content in these TTGs. And what they show, they basically have temperature isocliffs for the titanium saturation at different pressures. So here we have 950 degrees at 1.5 GPa and at 2.5 GPa. And then they plot the natural data on top. And what you can see is that the majority of the natural data falls between 750 degrees and 950 degrees. So this, for me, I thought was really a really neat way of showing that the titanium saturation temperatures would definitely say that it's low-ish temperature melting of basalts. So that's exactly what I'm saying. So to go on a bit of a deviation now from the petrology and all of this, I just want to think about the tectonics, because honestly, nobody knows what was happening with the tectonics in the Archean. I won't pretend to know, but I think it's important to think what kind of tectonic situations were the TTGs actually made in. So a lot of people would like there to be some sort of subduction or underthrusting in the Archean, where you have one plate being thrust underneath the other in a situation very, very similar to today on the modern Earth. And we have water dehydrating from the downgoing slab and partially melting this area to form our TTGs. Another idea could be that many Archean TTGs are actually sourced from plume activity. In this case, it's a bit of a complex scenario, but a mantle plume underneath the crust basically allows these basaltic or ultrabasaltic magmas to percolate through the crust, where the heat from the plume continues to partially melt the lower crust. You also have infiltration of material from the mantle plume. And via fractionation and mixing, you essentially form these TTGs. Ooh, wrong way. Another interesting question is delamination, which I think a lot of people like, which is where you have basically the lower lithosphere dripping off, which allows it to go to higher temperatures. You have partially melting of this material, and then you can basically fractionate through to create your TTG. Or another one, which is very popular in the Archean, is the formation of an oceanic plateau. So in an oceanic plateau, it would have been formed probably by mantle plume activity, which is erupting lots of material onto the surface. And just by burial, just by the thickening of the plateau, basically these lower areas of the plateau can melt, partially melt to form TTGs. So in all of these situations, this purple stripy material here would essentially be greenstone material. So it would be ultramafic and mafic rocks. The question is though, what is the source of free water for all of this? Like, how do we get the free water to the basalts to make the TTGs? So a question is, could it be the basaltic rocks themselves? Do we need an external source of water? Or can the basaltic rocks, if they're hydrated and metasomatized, actually give that water themselves? And the answer generally is probably not. So these are two phase diagrams from Porto et al. Just for a mafic basaltic rock. And basically, if we look to the right here, what we can see is we have bulk H2O content on this x-axis ranging from 0 to 6 weight %, and temperature is increasing on the y-axis, and it's at a set pressure. So this is at 0.9 GPa, which is probably a fairly good pressure in the crust to think about basalt melting. And basically, you can see is that this sort of red dashed line is the solidus, and this over here is the hydrated solidus. And these other very red fine dashed lines are melt fractions. So how much melt can we extract from the basalt at a given temperature and water condition? Now, basalts themselves, when they're metamorphosed at these conditions, you can see over here, they create basically amphibolites. You know, they're amphibole dominated, maybe with a bit of garnet, plagioclase, kind of pyroxene. But amphibole is the only source of water. It's the only hydrous mineral in these rocks. So it basically means that these kind of metamorphosed basalts can't have more. There's no way they can have more than 2 8% water. They should really only have 1, maybe a bit more. So you can see if we look at 1 weight % H2O here, at these low temperature conditions between, you know, up to 850, 900 degrees, you don't produce any melt. Above that at higher temperatures, you can start to produce melt, but you produce low volumes, so maybe 10, 20 volume %. So I think, you know, in general, I don't think the basalts, while they probably help via amphibole dehydration melting, they're probably not the source of water. So of course, the answer is going to be ultramafic rocks. Everyone loves ultramafic rocks. They're very good at soaking up water. But in the Archean, we didn't have maybe peridotite. We don't know, but we don't think we had the sort of ultramafic rocks we have on Earth now. But what we did have are komatiites. So komatiites are plume-sourced lavas. They erupt. And they have extremely high magnesium contents, over 18 weight %, but usually more like 25 weight % magnesium oxide. They have really high eruption temperatures because they're sourced from these plumes, up to 1700 degrees Celsius. And we find them in greenstone belts. The interesting thing is we mostly find them in the Archean. There are some younger examples, but basically most of the komatiites we find are from the Archean in the Earth because they're a signature of a much hotter mantle back then. So many of these lavas are erupted underwater, so they're therefore almost immediately hydrated by serpentinization. So on the bottom left, I have an image from the Pilbara Craton in Australia. This is actually basaltic komatiite, but you can see these are pillow structures. They're the ancient remnants of this basaltic komatiite erupting and then being serpentinized on the seafloor. When they erupted, they would have probably definitely contained abundant coarse olivine. So this is a picture of a komatiite in all these really long elongate sections you can see, what we call spinifex textures. So they would have been olivine crystals. And because they cool so fast, they most likely had interstitial glass, some pyroxene, some spinel, these kind of things. if we look at their chemistry, this is what we call a Jensen diagram, which is used to sort of identify these types of rocks. So you can see all of these data points here are from a global geochemical database, which I'll keep coming back to, which is from Gard et al. 2019, and it has about 5,600 individual geochemical whole rock analyses of komatiites and basaltic komatiites. So it's a very large and very powerful data set. So you can see they all plot towards very magnesium contents here, with komatiites being more magnesium rich than the basaltic komatiites. And just to compare over here, you can see the tholeiitic and alkaline series. So we're really moving away from aluminium, iron, calcium, all of that, to very much magnesium dominated chemistries. So as I said, I touched on greenstone belts before, but just to touch back on them if you're not familiar. We find these komatiites in greenstone belts, which are the sort of slivers in between our TTG domes. And this is just a stratigraphic log of a very famous greenstone belt, or part of a greenstone belt, which is in the Barberton terrain in South Africa. And sort of just to point out, these darker green is units that are very much dominated by komatiites. The lighter green is more basalts, the tholeiitic basalts usually. And then they're also interlaid with some other interesting things. So you get a lot of felsic volcanics, like dacitic, which is here in the purple, as well as some tuffs, and sometimes also banded iron formations, sediments, a lot of cherts. So they're very much sort of indicate like a in the ocean floor formation. And just as a little sketch I made just to sort of think about how these things are made, you know, we're under the ocean, but we probably have lots of eruption centers. And these eruption centers would be erupting the tholeiitic basalts, the basaltic komatiites, the komatiites, which are immediately serpentinized and hydrated by incoming H2O. And then, you know, in periods of quiet, they'll become interbedded with your sedimentary rocks, felsic rocks, etc. So if we look at our komatiites and basaltic komatiites worldwide, this is again this data set, this 5,600 analyses data set, and we can see where they fall. And of course, they fall in the Archean cratons that you can see in grey. So there's some very famous ones in Western Australia, South Africa, India, and also the Superior Craton. And I believe you actually also have some here in the North China Craton. If anyone's working on those, please let me know. I don't have any komatiites from this area, and that would be very fantastic. So as I said, they would have originally been olivine rich with these large spinifex grains, but of course now they've been serpentinized, and after that they've been metamorphosed. So most greenstone belts are metamorphosed to green schist or lower amphibolite facies. So here is a microscope image on the left, and you can see all these elongate clear sections. That's where the old olivine spinifex would have been growing. But now it's been replaced by serpentine, mostly antigerite, and chlorite. And in between all of the crystals, you can see this dark matrix, which probably was once glass, which is now a mixture of amphibole, chlorite, and magnetite. And the amphibole is usually tremolitic, so calcium and magnesium rich. And immediately you can see, I mean, the serpentine and the chlorite have 12% water in their crystal structure. The amphibole has around 2. So immediately you can see this is an incredibly hydrated rock type. And they also have a lot of other accessory minerals and things. These are some other nice examples I thought I'd show. These are also microscope images. On the top, these 2 samples are from the Yilgarn Craton, which is in Australia. And these actually have relic olivine. So these long elongate olivines you can see are actually the relic erupted spinel olivines, which is pretty cool. But they tend to alter and then be metamorphosed to form antigerite and chlorite rich assemblages. This is an example from the Shingwum Craton in India, which looks a bit different because it's higher grade. It's actually amphibolite facies. And here you can see a lot of amphiboles, but also these sort of glomerates of antigerite and chlorite. And then this is an example from the Abitibi Belt in Canada, where you can see these long green areas, very pale green, are again the old spinifex. They've been replaced now by antigerite and quite abundant chlorite in a matrix of more amphibole, more antigerite, more chlorite. So generally they don't have the most exciting mineral assemblages. They all look like this, but it's kind of nice because it shows us that yes, they were all definitely hydrated at some point, definitely most likely in the Archean. And of course, we wanted to quantify how much water they have. So this is just 6 samples from around the globe I chose. And this is water content here on the left. And this is just their water budget. So you can see they have between 3.5 to almost 9 weight% water. And the key thing is actually that a lot of this water is in the chlorite. So chlorite in purple accounts for a lot of the water budget. Antigerite usually a lot as well, or a bit less. And then of course amphibole a little bit less, considering it only has 2 weight% water. So a bit about their mineral chemistries. This is just the mineral chemistry as measured by EPMA. On the x-axis here, we have the XMG, and then on the y, we just have aluminium. And I just wanted to point out how high sort of magnesium numbers these minerals have, going all the way up to 0.93 in the antigerite. The chlorite too has incredibly high XMGs, usually around 0.9 to 0.91. And this will be important later, so I'll come back to it. If we now look at the whole rock database, so this is this database of 5,600 bulk rock chemical analyses, we sort of see the same trend. This is also aluminium versus XMG, but now it's bulk rock analyses. And I find this really cool. So each analysis is color coded for LOI. So in this work, we use LOI as a proxy for basically water content. It's true that the LOI can also include carbonates and other volatiles, but in general, we take it to represent the water content. So these more purple colored analyses are the basalts. They have much, much higher aluminium than the komatiites, and they also have a lower XMG. They have less magnesium and more iron. So they plot down here. And the komatiites tend to have more like LOIs over 5, so they go into these more orange and yellow colors. And you can see that they really nicely form a trend between the LOI, aluminium, and XMG content. If we now flip this around a bit, so now I'm plotting LOI as a proxy for water here on the y-axis and looking at XMG on the x-axis. These points are just means of the data I showed you before, the whole rock database. And you can really see the incredibly well-defined trend with the basaltic komatiites down here having water contents of maybe only 2 or maybe 3 weight%, and the komatiites, which have an XMG usually above 0.8 also, having water contents in excess of 5, 8, up to 10 weight%. So this is a really nice way to show that even though we have these basaltic komatiites and we have basalts, it's really the komatiites that are holding the water budget in the solid earth in the Archean. And this is just the number of data to show you how large our data set is essentially. And of course, the reason why komatiites have so much water is because they have such high proportions of antigerite and chlorite. The basaltic komatiites are essentially amphibolites. They're full of a lot of amphibole, but it's the antigerite and chlorite that really makes this incredibly hydrous. We can also define that as a relationship. So again, now I have aluminium versus calcium, and this again is the whole rock database, which is color coded for LOI. And the relationship with LOI is so strong that you can actually calculate a 3D plane through this plot and you get this relationship. So the LOI in komatiites and basaltic komatiites is more or less directly proportional to this equation. So just to really hammer home how strong this relationship is. So that's all well and good. So we've looked now at how much water komatiites have. These are the komatiites that are preserved in the geological record. They're only green schist amphibolite facies. But the question is, what would happen if we kept metamorphosing those rocks? So I calculated some phase equilibria models, of course, as a petrologist, I think I have to. And these phase equilibrium models are like a map through PT space of the different mineral assemblages you would expect. So we have pressure here on the y-axis and temperature here on the x-axis. And these are all the phase phase topologies. So right now in our green schist amphibolite rocks, we're probably sitting in here in this tremolite antiquarite chlorite field. But if we continue to metamorphose those rocks, they would undergo dehydration as temperature increased. And that's what these colored lines here show. So basically you start down here releasing around 1 weight% water, and you progress to the yellow when you release 6 weight% water total. And that occurs via 3 main metamorphic reactions. Down here, we have antiquarite out quite early at about 550 degrees, which is similar to when antiquarite breaks down on the Earth today. We have a second reaction, which is between the blue and the green, which is tremolite and chlorite out. It's sort of a progressive reaction. And then we have a final reaction, which is highlighted in the oranges and yellow colors, which is the terminal chlorite breakdown. And this happens at 800 or so degrees, which is quite amazing. Well known if you're a mantle petrologist, but if you're not a mantle petrologist, it's always quite amazing that chlorite can persist at such high temperatures. But this is completely due to its XMG, as I pointed out before. The higher the XMG of chlorite, the higher the temperature it can persist to. So if we look at that across a thermal gradient, so this purple color is a thermal gradient in the Archean. It's about 950 degrees per GPa, which is like an average thermal gradient for the Archean, as an example. And that's what I've plotted along here. So on the y-axis, we have the amount of fluid released in weight%. In this case, it's water. And then along here, we have the increasing thermal gradient, and we cross all of these reactions. So as I said, the antiquarite out reaction down here is releases a bit of water, but it's really the breakdown of chlorite and tremolite up to about 750 degrees, which releases the bulk amount of water. And that releases about 5 weight% water at quite high temperatures. What about carbon dioxide? If you've ever been to a greenstone belt, you notice there's a lot of calcite hanging around, a lot of carbonation. So we also wanted to investigate that. So we chose a XCO2 of 0.1 to investigate. So in this case, that corresponds to around 2.8% CO2 in the rock. So you can see that the calculated phase diagram is a little bit more complicated, but we sort of have the same main breakdown reactions, just with also calcite and dolomite breakdown. And of course, when calcite and dolomite break down, they'll release the CO2. The good thing is that if we look at this plot here, we have water alone, just pure water in the dark pink, and then CO2 on top of that in the light pink. We can see that most of the CO2 is actually released at temperatures below 700 degrees. Most of it's actually released below 600 degrees because there's a terminal dolomite out reaction at around 600 degrees. And that's kind of useful because CO2 can really suppress melting. If you have a really high CO2 fluid, any associated melting will be suppressed. So the CO2 is definitely released on the prograde path of these rocks. And then they still release significant water, a little bit less, maybe 4 weight%, 3.5 weight%. And they release this water again over 700 degrees Celsius along the same thermal gradient. So now I think I've given you a lot of evidence, different facts, different models, different data. And I'd like to sort of put all these lines of evidence together because just to show you that it's really, I think it's very possible that komatiites are the source of free water for basalt melting in the Archean. So here we have our phase diagram again with pressure and then temperature. So here we have the probable maximum thickness of the Archean crust. That's a bit debated. It depends who you listen to or who you like, but it probably wasn't much thicker than about 45 kilometers. In the colored lines, I've put those release of mineral bound water from the first phase diagram. So the diagram that had water only, showing from 0 to 6 weight% water release as you go up temperature. Just to compare, if you remember these last lines here, this is the terminal chlorite breakdown. Here are also some experimental chlorite breakdown temperatures. These are from more modern rocks, but just to show you that chlorite can really persist to higher temperatures. And if the chlorite has a higher XMG, which is possible, then the chlorite will actually persist way up to 900 degrees maximum. Now what I've put on is a data set from Brown and Johnson, and some of you might be quite familiar with this data set. It's the PT conditions of metamorphic rocks, and in this case, I've filtered the metamorphic rocks in the Archean. So each of these pink points represents the maximum PT of a rock analyzed from the Archean. And I think this is useful because what this tells us is that these are the crustal conditions of metamorphism in the Archean. Like this is the PT area that rocks are being metamorphosed in. Therefore, if a komatiite was to be metamorphosed further than the ones we have now, that it would probably, definitely be within these sorts of conditions. So we can kind of cut off the rest of the diagram, and you can see here this 950 degrees Celsius per gigapascal. This is the mean I calculated from that data, the mean thermal gradient recorded by Archean metamorphic rocks, and it corresponds to about 30 degrees per kilometer. So each kilometer you go down, you increase 30 degrees. And this is a bit warmer than today, but I think it's reasonable. Then on top of it, I'll plot the wet basalt solidus. So this is the solidus. This is the point where if a basalt crosses this in the presence of water, it will begin to melt. There's a lot of wet basalt solidi out there. I've just chosen this as an experimental one from the 70s. I think it's pretty good, from Lambert and Wiley. And immediately you can already see that these later stages of dehydration from the komateites fall above the wet basalt solidus. So if a komatiite and a basalt are interlayered or juxtaposed or interacting somehow in the Archean, the dehydration of the komateites at these temperatures will immediately trigger voluminous wet melting within the basaltic rocks that are nearby at the same pressure temperature conditions. And just for some interest, if you remember the titanium saturation temperatures I showed you before, those are from TTG, so the products of the melting. I plotted them on here, the sort of general range from 750 to 950 degrees Celsius, which you can see here in gray. And this is interesting, I think, because these range of temperatures is slightly higher than the dehydration reactions in the komatiite. The dehydration reactions in the komatiite are maybe occurring between 650 and 800 degrees, but that's below the general melting temperatures that our TTGs tell us. So whether what that means exactly, I don't know, but what I think it could mean, a very big possibility, is that when you're prograde metamorphosing your basalt and your interlayered komatiite, you hit this section, you start dehydrating everything, you start melting your basalts, but burial continues. So the temperature keeps increasing after that. So it means that actually, while the water is released here, the bulk of the melting and the bulk of the TTG formation actually happens at slightly higher temperatures, which is a possibility. So just to really summarize all of that, if we're looking along this 950 degree thermal gradient, I've now plotted on the CO2 and water release and just the pure water release. You can immediately see that at average Archean thermal gradient, the bulk of this water release is above the wet basalt solidus, and the wet basalt solidus is just the same as this solidus here. So at about 680 degrees. Before that, lots of the CO2 is released before we hit that and probably taken out of the system, but the majority of the water as released by tremolite and chlorite breakdown is above the wet basalt solidus. So how exactly would this look? Like, this is something I don't know. So this is all conjecture. This is all just ideas now. But if you remember, I showed you this nice stratigraphic column before from the Cartval Craton. There's also some other ones here from the Shingbum Craton in India, the Pilbara Craton in Australia. You can see the komateites in this vibrant dark green are interlaid with basalts. So these Light green sections are sort of tholeiitic to high magnesium basalts. And they're of course created in this sort of scenario here. So if you were to bury one of these greenstone sections, I think it would make a lot of sense for localized melting to occur. So you'd have the immediate dehydration of the komatiites into the overlaying basalts, and you'll be melting sort of in situ. And once these partial melts are voluminous enough, they escape, of course, to make these big TTG columns. The problem is that this part of the geological record is missing. We have the low-grade greenstone belts, we have the TTGs, but we don't have any evidence of this sort of greenstone material being melted. We don't have the cumulates, we don't have the residuum. And I think that's because they're incredibly dense. So they're probably, delaminated from the crust, they may be subducted, who knows, but they're now lost from the geological record. They're essentially in the mantle. And I think it doesn't help that we also don't have much material from the Archean to actually study. Archean crust is incredibly rare. So while this intermediate stage is missing from the basalt to TTG cycle, I think we can try to make some inferences from, looking at the geochemistry, etc. So just to summarize, as I said at the very beginning, the modern day production of the continental crust, as we know, is diuretic to andesitic in composition. And it's a water-driven process. It really is. Like, without this subduction zone, without this water being pumped up, we really wouldn't have the arc and we wouldn't be making all of this continental crust. And in this situation, basically, the release of water is mostly driven by antigrite breakdown and chlorite breakdown in the subducting slab, with of course, some help from the metabasites, lawsonite out, epidote out, etc. But also maybe the sediments as well probably play an important role. So I'd like to say in the Archean, it was the same thing. The ultramafics, these dehydrating komatiites, were the source of water, and they played an incredibly important role in the formation of continental crust. So here's my sketch before of possible Archean tectonics. And in the green, I've highlighted very generally the conditions of tremolite and chloride out. And this tremolite and chloride out reaction, which releases 5 or so 8% of water, would hopefully be the way to make our continental crust. So a last take home, the Archean komatiites, which I showed you, which look something like this, may be quite similar to modern day peridotite. This is an example drilled from the mid-Atlantic ridge, which is an ocean ridge, showing, a very serpentine and chlorite dominated assemblage. There's also some future directions. I'd like to quantify some of these volumes of komatiites and the volumes of water release. And I'm quite interested in coupling komatiite dehydration and basalt melting in phase equilibrium modeling to see if we can further this idea. And with that, thank you very much for the invitation again. Thanks for listening, and also thanks to some of my collaborators. Thank you.
Okay, thank you, Renée. Now it's time for questions from our participants. So feel free to open your mic to ask a question or raise your hand before you ask a question. Or you could also post your question in chat, and I could read a question on your behalf. So any questions from our participants today?
No, they're all in shock.
Renée?
Yes.
I'm Jiasheng Hu. It's a very good talk. I learned a lot. I'm doing geodynamics, so probably I will ask some very very basic questions. Yeah. The first thing I have, my question is, you mentioned that the formation of the TTG is at a higher temperature than the temperature where the dehydration occurs, right? Mm-hmm. You said this probably because the melt of the water will remain when it's kept buried to deeper depth. Mm-hmm. I'm wondering why this explanation is not straightforward to me, because I think if a plumes come in to raise the temperature, seems a more straightforward way to raise the temperature, right?
That's true. That's a very good point.
Yeah, you don't have to bury it gradually.
No. You're right, you don't. There can be other sources of heat as well. You're completely right. So that was a bit of just a bit of a guess. 1 minute. The only reason I say that is not very, sorry, is basically because of water saturation in the melt. So I think you're right, you don't have to keep burying it, but I think the increase in temperature is kind of important because when you first, this is a diagram similar to before, and the komatiite dehydration is shown in the gray colors. So this is 5%, where that's 5% where this gray line is here. And essentially, if you release all your water at that point, the resulting TTG can have around 6 weight % water in it. But that might not be a super voluminous TTG. That might only be, I don't know, like 10 volume % melt, maybe a bit more. If you want to increase the volume % melt, you basically dilute the water so you can go up to higher temperatures. You create more melt with less water in it, and then you're actually able to make really voluminous things that can perhaps leave the system. Not varied in logic, but that was kind of one of the things I was thinking about. But I definitely agree with you. It doesn't have to be that. It can be an external source of water, such as of heat rather, sorry, such as a mantle plume or maybe more melt coming from below. You can absolutely do that. Thank you.
Yeah. Actually, I mean, if you want to have a Pluton, I thought you will have a lot of melt, right? So
yes, exactly. Well,
yeah.
I think you have to partially melt everything. So maybe you only make 20%, 15% melt locally, and then the melt has to escape, right, to actually form the Pluton. So there's kind of like an intermediate stage there. And that's when a lot of this mixing can occur. And that's also when a lot of fractionation can occur. So there's a middle step between partially melting your basalt and making a huge plume. And that's actually accumulating all the melt together.
I see. Yeah. Thank you. I mean, it's a very nice talk. Thank you.
Okay. Thank you very much. And thanks for the question.
Okay, next question, please.
Hello, Renée. I have a question. So, yes. So, have you calculated the water budget of, for example, how much water can the komatiite generate, and how much water is preserved in the TTG, based on their volume or mass on the Earth?
Yeah,
and
that is a really good question. I would really love to do that. That's hopefully something I will definitely do in the future. And right now I can kind of do it because I can look at these stratigraphic logs and I can say, okay, we have, X kilometers of komatiite or X meters of komatiite, and that komatiite has 6 weight % in every cubic centimeter or whatever you want to do. You can absolutely do that. The question for me is how representative are the Archean cratons? So if I do that, if I calculate the amount of water held in the greenstone belt, and then I look at the TTG, maybe one big batholith, and I say, how much water did this need? That's okay, but putting it into the mass balance of all of the Archean crust, I don't know, because the TTGs have a high preservation potential, I think. They're very buoyant, they're very resilient, they're much easily preserved in the geological record. But the greenstone belts I think, have a lower preservation potential. So we don't know how much greenstone belt there was. So there's sort of a missing piece of information, but I think it would be a really good idea to do that in the future. Definitely.
Yeah. Thank you. Very good talk. Thank you.
Thank you.
Okay, there's another question in the chat, and I'll read it for that. So, so for this komatiites, they get hydrated to contain high water content in Archean or in Phanerozoic.
Yeah, brilliant question as well, because I didn't look at any geochronology. I just said they get hydrated immediately. Yeah, you're right. There's barely any geochronology. They're very hard rocks to date, and it's very hard to date the hydration. That's also one of the aims of my project. I'm starting to have some luck with epidote. So using epidote to date the timing of metamorphism, at least, which says that the hydration had to be before the metamorphism. There is one paper that came out in 2022 by Robert Bolha, he's at Wits University, and they dated the hydration. And basically they used titanite geochronology. So titanite formed during very low grade metamorphism hydration. And the age they got from that titanite was indistinguishable from the eruption age. They had eruption ages from interlayered gabbros that they could date, and then they had the timing of that. So that's only one example of when the hydration was just immediately after eruption. But hopefully if I can do some more geochronology to really show that they are hydrated in the Archean and hopefully not the Phanerozoic. But a lot of them were erupted underwater. So I think that's a good piece of evidence that they must have been hydrated upon eruption, because serpentinization is a very effective process. I hope that answers your question.
Okay, next question, please.
Hi, Tamblyn. Can you hear me?
Hi.
Hi, I'm still a PhD student, and nowadays I really like your work. And actually, I had a presentation on the seminars about your work. I just read your paper. I think it's a very good idea. But basically, it's about a question about the pathogenesis of TTG. Why would we need so much water? Because basically, I just think the white basalt is enough to produce volumeless TTGs. I really have no idea why would we need so much water, this so large a water tank. I want to hear your idea, actually.
Okay, yeah, thanks. It's an interesting question. So I don't know if there's, that's a really thing. Everyone says you need water, and they say, yeah, you need lots of free water to make the basalts, but often they don't say how much. And if you look into the experiments and you also look into the phase equilibrium modeling, it's actually not that much water. It's usually a couple of weight %, 1 or 2. So the komatiites make 6 weight %, but the basalts only need 1 or 2, which I think is cool, because that means you only need a little bit of komatiite to hydrate a lot of basalt. With the amphibole, so with the dry basaltic, well, not dry, but the amphibole breakdown melting, I think I have a picture of that. 1 minute. I have a lot. So these are some diagrams showing the melting of a basalt with just a tiny, tiny bit of free water. So the one on the left has a lot of free water, and the one on the right, I think, has slightly less. The problem with having no free water is that you just make really low volumes of melt. So these sort of dashed lines are the melt volumes, and these have water in them. So essentially what you do is you have 1 or 2 weight %, and at 800 degrees, you've already made 17 volume % melt, which is great. Same in this diagram. At 800, I think you've made only about 7, but still. But if you have dry conditions, and I don't think I have a diagram for that, unfortunately, I don't. But usually via the amphibole dehydration melting, you'll only make a few % melt, maybe 10 maximum at these conditions. And you can do that, that's fine. There can also be that type of melting of basalts. But if you want to make the insane volumes, like some of these TTG plutons are huge, the amount of basalt you would have to dry melt would just be insane. It would just be incredible amounts of basalt. Whereas if you have the water, it means you need less basalt and you can do higher degrees of partial melt at lower temperatures. If that answers.
Thank you. Thank you for your answer.
Yeah. Okay, no worries.
Any more questions? Okay, if we don't have more questions, could everyone open your video to show your appreciation for our speaker today before we turn the video off? So Renée, could you stop sharing your screen so you see more faces that participated?
I will. 1 second, stop share. There we go. Hi, everyone.
Okay, I think we'll turn the meeting off in about 30 seconds. So
Great. Thank you very much again for the invitation. I appreciate it.
and thank you for your talk, and thanks everyone for your participation and the questions from some of our participants.
Yes, thanks for the questions and for coming.